Hello, my name is Mr. Pratt, Director of Science, and we're on to the third lesson on the GCSE Forces topic. Today we're going to look at mass and weight. Before we move on, in lesson 1 I said I'd ask you again about the 4 scientists that you can see on the screen now. So top left we've got Johannes Kepler, who studied the orbits of planets and put together the maths that describe orbits, particularly orbits that are not going in circles, that are going in ellipses, ovals. Bottom left we've got Robert Hooke from Hooke's law, which you'll see in probably the next lesson, stretching a spring. We've got Albert Einstein, who did loads of things, but one of the things he looked at was explaining what gravity really is and linking gravity to acceleration. And then we've got the man that devised pretty much all of the applied maths that we use and the laws that we still use that govern motion now, Isaac Newton. For this lesson, you're going to need the usual: a pen, paper or an exercise book. Going to need a calculator, quite a few calculations to do today. And unless you're needing to use your mobile phone to watch this video on, get it out of the way, turn it over, get it on silent, avoid as many distractions as you can. All right, starter then. 3 things for you to do. You might not get time for the third one. I'm going to give you 2 minutes. List 3 scalar quantities, 3 vector quantities. That's looking back to lesson 1. Explain which of 2 objects would fall more quickly, the football and the balloon. Assume they're both the same size. Number 3, if you've got time, draw a free body diagram for the falling ball and the falling balloon. Halfway through your time. Let's see what you've got on. So 3 scalar quantities first. There's quite a few that you could have had. I've just put 4 down here. So distance, speed, mass, time, energy. And then 3 vectors. Well, I've put to start with the 2 vector equivalents of distance and speed, which is displacement and velocity, and then force and acceleration. So remember, with all the vectors, it's not just the magnitude, the number that matters, it's the direction which we mark of an arrow. So vectors have both magnitude and direction. Scalars, just magnitude. Second one. Now I'm going to do number 2 by doing the free body diagram, because that's the beauty of free body diagrams. They help you to explain what's going on. So the first thing that I'm going to do is mark the centre of mass of both, so roughly in the centre. We're assuming they've both got the same size. And if they've both got the same size, as you start letting them fall, and they're falling, so they've both just set off and they're falling at the same speed to start with, they both have the same air resistance because the shape is the same. But the difference is the ball has got a much greater weight than the air resistance. So if you look at the size of the arrows, the weight is much bigger than air resistance, so acceleration will be quite large. But with the balloon, the weight is only a little bit bigger than the air resistance, so you've only got a very small amount of acceleration, and the balloon would reach terminal velocity quite quickly. In other words, those forces would balance quite quickly and it would fall at a steady speed to the ground. What you've got to remember though is if we didn't have the weight bigger than the balloon to start with, it wouldn't actually start moving at all. It would stay as it is. So you've got to have a greater force down than up for it to accelerate down towards the ground. Now look at the outcomes for today. The initial outcome that we're going to do is just explain the difference between mass and weight, and I'm going to go over it and keep saying it quite a few times because once you get it, it's an incredibly useful bit of knowledge that you've got. So I will repeat myself a little bit. I'll apologise for that now. And then we're going to move on to calculating the weight, the mass and the gravitational field strength using the equation weight equals mass times gravity, and that's an equation that you need to remember for the exam. So we've looked at the difference between mass and weight lower down school in Key Stage 3, but it's very important that we understand it clearly and get it right. So if we do that first, and then we'll move on to doing some slightly more tricky calculations. So Simpsons, they've always been a massive hit. See what I did there? So I'm going to tell you the masses. So Marge, she's got a mass of 60 kilograms. Maggie 10. Lisa 25, Bart 35, and Homer 130 kilograms. That's their mass. So mass is always measured in kilograms. Mass is a measure of the amount of something that we've got, so it's to do with the number of atoms and what those atoms are. Mass doesn't change depending on where you are. So if Homer's got a mass of 130 kilograms and he goes somewhere else, he's still got a mass of 130 kilograms, unless he decides to lose weight, that is. So what is mass now that is in space? Don't get caught out. Mass doesn't change depending on where you are. Homer's mass stays 130 kilograms. So the Simpsons now are waiting for their favourite TV show to start. Weight's different than mass. Weight is a force caused by the gravitational field. All forces are measured in newtons. So weight is newtons, but mass was kilograms. And we'd mark weight just like we do other forces. Remember, forces are vectors, so we mark them with an arrow because we need to know the direction that they're working in. So we get arrows representing the weight, something like that. They're all on Earth there on the settee. Homer's got the biggest mass. Homer would have the biggest weight. But weight will be different if the gravitational field is different, because weight doesn't just depend on your mass, it depends on the pull of gravity as well. So what's Homer's weight now that he's in space? Weight depends on the gravitational field. So if Homer's in the middle of space, not near a planet, not near anything that's got any mass, the gravity will be zero. If the gravity's zero, he's got no weight, he's weightless. So his mass stays at 130 kilograms, but his weight is now zero. So in summary, pause the video if you want to record this. Weight is the force acting on an object due to gravity. The weight of an object depends on the gravitational field strength. That's how strong the gravity is in that place. And the mass of the object. Objects on the moon weigh less than objects on Earth because the gravitational field strength on the moon is less than it is on the Earth. Quite a lot less, actually. as Homer. Mass 130 kilograms. Might be increasing depending on his donut intake. Weight. So we've drawn his weight towards the centre of the Earth. Gravitational field strength on Earth is about 10 newtons per kilogram. In GCSE, they will ask you to use 9.8, which is a number closer to what it actually is. It will be given in the question though. So we're just going to use 10 now for now because the numbers are a little bit easier. This means that the Earth pulls down with 10 newtons on each kilogram. So if the gravitational field strength on the Earth is 10 newtons per kilogram, for every kilogram of Homer or anything else, there's a force of 10 newtons. And Homer has got 130 kilograms, not one. So Homer will be pulled down with a weight of 130 kilograms times the 10, which would be 1,300 newtons. So there's the equation. Weight equals mass times gravitational field strength. Weight, use the letter W, is measured in newtons, capital N. Mass, M, measured in kilograms, kg. Gravitational field strength, we use the little letter G, and that's measured in newtons per kilogram. So let's get you doing a little bit of work. You won't need your calculator yet because I'm picking easy numbers. So we're going to use weight equals mass times gravity. We've got the mass of the 5 of them on the screen. I'm telling you the gravitational field strength on Earth is about 10 newtons per kilogram, so we'll use that for now. I want you to calculate the weight of Marge, Maggie, Lisa and Bart on Earth. Halfway through your time. Right, let's see how you've done. I'm going to get you to mark it yourself and give yourself a mark out of 10. You'll see why it's out of 10 in a second. So the answers, Marge, 600 newtons. So there's 1 mark for your 600 and 1 mark for the newtons. So if you've got 600 newtons and you've put a capital N, 2. Maggie, 100 newtons, because it's 10 times 10. 1 mark for 100, 1 mark for newtons. Lisa, 250, because it's 25 times 10 newtons. Bart, 350 newtons, it's 35 times 10. And Homer, 1,300 newtons, because that's 130 times 10. So give yourself a mark out of 10. Well done if you've got that right. So different planets in the solar system each have different strengths of gravitational field. So the strength of the gravitational field that you find on a planet depends on the mass of the planet and also the density of a planet. So you might have a very big planet, but because it's not very dense, in other words, the material that makes it up is quite spread out, it can reduce the amount of gravity. So a really big planet that's made out of very dense material would have a very high gravitational field. You can make a rough guess based on the size. So imagine travelling around the solar system with a container of food, as you would. You don't open the container, but its weight would change depending on the planet that you're on, because the gravitational field strength changes. So I want you to use the equation, weight equals mass times gravity. I'm going to give you 2 minutes. I've given you there gravitational field strength in different parts of the solar system. And I want you to calculate the weight of a 0.5 kilogram bag of donuts in the 5 different locations shown in the data table. Off you go. Don't forget your unit when you've got your answer. halfway through your time. See how you've got on. So on the Earth, 5 newtons, 0.5 times 10 is 5. Moon, 1 newton, 0.5 times 2 is 1. 12 newtons for Jupiter, 2 newtons for Mars, 4.5 newtons for Saturn. Mark out a 10 again. Make sure you've got the units, otherwise you've just dropped 5 marks. Force is measured in newtons and weight is a force. So this is the main thing so far. We've done some basic calculations. We're going to come on to some more difficult calculations next. But the real important thing is you can describe the difference between mass and weight. Mass then, it's the amount of something. It's measured in kilograms and it doesn't depend on gravity. Weight, it's a force, so it's measured in newtons. And it depends on the mass of something, but it also depends on the pull of gravity, the gravitational field strength measured in newtons per kilogram. Now, so far we've calculated weight of an object using that equation. Now we're going to move on to calculating the mass or the gravitational field strength. So we've got a bit of moving about to do, a little bit more of a difficulty with our mathematical skill. Modelled example first, and then we'll get on with you doing some work. Astronaut stands on some kitchen scales on the moon. That is an actual photo of an astronaut standing on kitchen scales there. The gravitational field strength on the moon is 1.6 newtons per kilogram. So for every kilogram of mass, there's 1.6 newtons pulling it down. If the kitchen scales show the astronaut's weight as 144 newtons, what's his mass? First thing we do, write down the equation. So we'll write down the equation. Weight equals mass times gravity. Put in the values that you know. We know the gravitational field strength, G, and we know the weight, W. So we'll put them in. So 1.44 equals M, we don't know that, times 1.6. Now we need to get the value that we're calculating on its own, so we want M on its own. You can do what you like to an equation as long as you do it to both sides. If we divide both sides by 1.6, it means that on the right hand side, the 1.6 divided by the 1.6 gives us 1. So that leaves M on its own. So M equals 144 divided by 1.6. Put that in your calculator and we get a mass of 90 kilograms. Of course, that wouldn't just be the mass of the astronaut, it would be the mass of the astronaut and everything that he's wearing. It would probably be a good idea now, if you think that you need to, if your maths isn't super strong, just to pause the video and put that down as a model example, because you can use the method that we've done there when you're doing your next set of questions. Use it to help you do it the same way. It's just the numbers that will change. The way that we've done it will remain the same. I'm going to give you 4 minutes total here. First question's grade 4, so it's a basic one without much moving around, straightforward substitution. Then grade 5, we've got a bit of moving around, and then grade 7, it's a bit trickier. I'm not going to say any more about that. I'm just going to leave you to get on with it. I'm going to give you 4 minutes, and then under the visualizer, I'll explain the method that I've used and you can give yourself your marks. One minute gone. Just coming up halfway through your time, you should be at least halfway through question 2. If you do find, which a lot of you will, question 3 quite tricky, just try and follow the same method and try and get some marks. You might not get all of them, but that doesn't matter. Okay, if you have finished, just be checking you've got units in your answer, because that's going to be getting you some marks. And also, if you have finished, double check the grade 7 question number 3. There's something in it that you might have missed to do with that value for weight that they've given you. Let's see how you've done then. So first one, find the weight of a space tourist. So it's the weight we're trying to find. So I'm going to write weight question mark, or you could have put W question mark. We know that the mass M equals 55 kilograms, and we know the gravitational field strength, that's G. G equals 3.8 newtons per kilogram. Remember, the Earth is 9.8 because Mars has got a smaller mass, the planet's got a smaller mass. We've got a lower gravitational field strength. So we write the formula down. W equals mg, so the weight equals the mass times gravity. Weight we don't know, so we'll just write W. The mass, that's 55, it's 55 times g, so times 3.8. Pop them in your calculator, 55 times 3.8, 209. So the weight is 209. That's 1 mark you've got, but we need the unit. Weight is a force, so it'll be in newtons. There's a little reminder somewhere in the question there, the N there per kilogram. What that G of 3.8 means is you get 3.8 newtons acting on each kilogram. Newtons per kilogram. So we've got 209 newtons. So 1 mark for 209 and 1 mark for newtons. So that's out of 2. So give yourself a mark for that. Next one, grade 5 question. We do it in exactly the same way. So we're using W equals M times G. This time we know the mass of the rocket is 1,200 kilograms and the weight on the dwarf planet's surface, so it's on Pluto, is 756 newtons. So we know the weight and we know the mass. So we put those in underneath. So W, that's 756 newtons, equals the mass, 1,200, times G. And that's what we're trying to find. We're trying to find the gravitational field strength. So 756 equals 1,200 times G. What we want to do now is to get G on its own, so then we'll know the answer, because we'll get G equals whatever the answer is. So the best way to get G on its own is to divide that side of the equation by 1,200, because if we do that, 1,200 divided by 1,200 is just 1. 1 times G is just G. What you've got to then remember is we've got to do it on the other side of the equation as well. So we're dividing both sides of the equation, so 1,200. So G then, I'm just going to jump and write my answer over here because I've run out of room a bit. So G equals 756 divided by 1,200. 756 divided by 1,200. This gives us a value of 0.63. 0.63. Now that's worth 2 marks so far. Because we've had to do a bit more moving around, this one will be worth 3. So if you've got 0.63, you've got 2 marks, but you need a unit. Now it's a bit easier for us now because the unit's actually written up here of newtons per kilogram. But that G, gravitational field constant, means we get 0.63 newtons on every kilogram. 0.63 newtons per kilogram. So that's worth the extra mark. 3 marks if you've got that. Well done. It's a bit trickier. And then on to one that's a bit trickier still. So in question 3, we'll end up with an answer, but then we have to use the answer to look up which planet it's most likely to be. So we've got values of the gravitational field constant in different places there. Notice the unit is written differently here for G. It's written in meters per second squared. The two units do actually mean the same thing. I find it more useful to use newtons per kilogram because it explains exactly what's going on. It's a force on each kilogram. Let's do it the same way though. W equals mg. So what do we know? We know the mass. So the mass is 1,750 kilograms. So we know that. What else do we know? We know the weight, W, equals 6.21. Oh, that's kilonewtons. So that's not 6.21 newtons. So I'm not going to write that down. 6.21 kilonewtons means 6.21 thousand newtons. So I need to multiply that by 1,000, which is 6,210 newtons. There's 1 mark for doing that conversion straight away. 6.21 kilonewtons is 6.21 thousand newtons, or 6,210 newtons. So I'm going to put those two values in. W equals mg. So 6,210 newtons equals the mass, 1,750 kilograms, times g. And then once we've found G, we can see which of those numbers it's closest to. So what we do here, we want to get G on its own. So we divide both sides by 1,750, because if we do that, that over that just equals 1, so G's on its own. We've got to remember to do it on the other side, 1,750. So G equals 6,210 divided by 1,750. 6210 divided by 1750, 3.54857. I'm writing down more than I normally would just to show you. Here, over in this table, we've got 1, 2, 3 significant figures. So I'm just going to put that down to 3 significant figures here. There's not a mark for it in this question, but it's good practice to have. So if we need 3 significant figures, I need that one, and that one. So it's 3.5 something. But because that one after the 4 is an 8, so that's bigger than 5, we need to round up so it becomes 3.55. So 3.55 newtons per kilogram. So now you've picked up another mark for that one and another mark for that one. So we've got a mark for the conversion, a mark for the number, a mark for the unit. Actually, I'm not sure as they give you a mark for the unit because it's in that table, but I'll let you have it. We just need to then go across and find the number that it's closest to. So 3.55, so it's not that one, not that one, not that one. Well, we've got a 3.75 for Mars, and we've got a 3.61 for Mercury. So the closest one is actually Mercury. So you get 1 mark for writing Mercury as well. If you just took a punt and put a guess down and written Mercury, you'd still pick up your mark. If it was a little bit inaccurate, there's a good chance that it could actually have been on Mars if there was a little bit of error in those readings. So well done. Add up your marks out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's out of 9. Anything more than 4, well done. On from that, onto an exam question there. You'll probably find this a bit more straightforward. It's read about a grade 3, 4 exam question. Important nonetheless, because these are the ones that we really need to get right, all of us. So I'm going to give you 2 minutes. It's worth 4 marks in total, and then you can self-mark your own. Right, self-assess it, yourself a mark out of 4. We should be looking at getting 3 or 4 marks on this one. First question. Force is a vector. Which of the correct statements about vector quantity? It's got a direction and a magnitude. That's what vectors are. So it's got a number, that's the magnitude, and we have to say which way it's acting. 1 mark for that. Make sure you've only ticked 1 box. Part B. They've kindly given you the version of equation which is easy to use. They've moved it for you, so mass equals weight divided by gravitational field strength. We just need to substitute numbers in and remember the unit here. So mass is 6.4 newtons divided by 9.8 newtons per kilogram, which gives us an answer of 0.65 for 1 mark, kilograms for the second mark. Last one. Mass of a bag of sugar is 1 kilograms. On Earth, the weight of this is 10 newtons. On Mars, the weight is 4 newtons. Suggests why the weight of the bag is different on Earth and Mars. So the mass hasn't changed. The change in the weight is caused by the change in the gravitational field strength. If you've just put gravity's less on Mars, you've nailed it. 1 mark. A little quick 1 minute to finish us off. All I want you to do on A, B, C, D, E and F is just to say whether that sentence is describing mass or describing weight. If you're not sure about any of them, just take a punt because the answer's either mass or weight. Don't leave it blank. Right, see how you've done. Constant no matter where you are. I don't know whether that's supposed to be a pun or not. Mass changes when gravity does. Weight measured in newtons. Weight measured in kilograms. Mass depends on the amount of matter present. Mass and depends on matter and gravity. Weight. Right, I'm going to leave you with a summary. How many of you can remember the names of all 4 scientists there, including the first names? So mass is measured in kilograms. Mass is the amount of something. Mass doesn't depend on where you are. Weight is a force. Weight's different depending on the gravitational field. We've got the equation and I've outlined what each of the symbols means. If you need to make more notes because you've not got a record of any of that, pause the video now and record it. If not, I'll see you next time. More forces lessons to come.